Good evening. I hope you're doing well. Today I came up with another topic which may be a continuation to the previous topic that I have posted already, that is about governing equations. So the governing equations which were discussed will end up with a final remarks of the equations, and then a kind of understanding of the equations, and then that equations we're going to use fully in this particular topic. So this topic is called DC motor operating characteristics. So by the name itself you can understand that it is something to do with the operation of a DC motor. Yes, you are listening it correctly. So when we see the DC motor, it is actually a very simple motor. Though it has commutator, the characteristics of DC motor is much desired, much appreciated in many of the applications. Okay, so that's why if you see the characteristics of DC motor, and then understand it, it's going to be very easy for you to understand any of the motors, because this will give a foundation to understand about the variation of speed and torque, variation of speed and armature current, and variation of speed and variation of torque and armature current. The basic idea, basic methodology of taking or tackling any motor's characteristics can be easily understood here. So by the end of this session, I hope you would be able to understand about the behavior of a DC motor with respect to the load. You are listening it correctly. So you're going to see, by the end of this session, you're going to understand the working of this DC motor fully with respect to the loading condition. Let us say when there is zero load, when there is 50% of load, when there is 100% of load, how the motor will actually respond, how the motor will actually react to that. If you want to know about it, you have to listen to this particular topic. So to give the complete idea about what is going to happen with respect to the every parameter of a DC motor, we have got three different characteristics given. Number one is about torque and armature current. Number two is about speed and armature current. Number three is about speed and torque. Okay, let me list them down now. Number one is about torque versus armature current. I'm going to detail them. Number two, speed versus armature current. Number three, speed and torque. I usually ask this particular topic in different questions. So I may ask the question in the examination something like, explain the characteristics of torque and armature current of a DC motor, or speed and armature current of a DC motor, or even the speed and torque characteristics of a DC motor, or I'll mention the specificity of the motor, whether it is a shunt motor or a series motor. Anyways, so this is how three different characteristics we can find. The first one is about, I'm going to explain them in detail. The first one is about the torque, variations of torque with respect to the armature current. Very good. And now the second one is about variations of speed with respect to the armature current, and third one is about variations of speed with respect to the torque, or it is even vice versa, variations of torque with respect to the speed. Somehow these are all the three different characteristics which we'll be focusing today. So the first one, we'll take the first one. So in the first and second ones, there is a commonality there. The commonality is that torque and speed are output parameters, and the IA, what is IA? It is an input parameter. So how much amount of current the motor is drawing from the supply. So these two are about the relationship between input and output parameters. I hope you're getting me. So let me first focus on the first one, torque and IA, and then I'll go to the next two also. So torque and IA are actually, it is very easy aspect of dealing with this first one, right? It is very easy. So what I do here is I'll take a shunt motor and series motor at the same time, so that I can easily understand about both of the motor without any confusion, without any issue of comparison, right? You can have a nice comparison. You can easily understand the aspects of these two motors with respect to the first characteristics, right? So the first one, the first motor, I'll take this side, I take as a DC. Yeah, I take shunt motor, and then to the right I take DC series motor. So now I'm going to make a line between them so that I can easily differentiate them. Fine. Okay, right. Anyways, so torque and IA. In the topic that I have already discussed, governing equations, I gave the equation between torque and armature current. Okay, torque and armature current. The equation that tells that is between these two goes like this. So torque is proportional to phi Ia. You know, why am I giving this equation? How can I tell about the variation of torque and torque with respect to Ia unless and until I know the equation between torque and Ia? So if I want to comment anything on the equation, on the behavior of torque with respect to Ia, I would always have to depend on the equation of torque and Ia. That's why I took the equation which is between torque and Ia. All right. Okay, so the same equation, just I'll take the same this side also. Fine. Okay, so now we'll try to analyze about the variation of torque with respect to Ia, right? So if I have to understand about the variation of torque with respect to Ia, let's see that. You know, when Ia will change. When Ia will change, what are the conditions of Ia to change in a DC motor? Ia will change only when there is a change in the load. You have to understand this point. So listen to this carefully. Whenever you take any of the characteristics of this particular DC motor, you're going to analyze, or you're going to see the entire characteristics with respect to the load. So when there is a change in the load, as I said in the beginning itself, when there is change in the load, how the motor behaves or responds to that. So if I'm making, if I say that Ia is changing, Ia doesn't change like that. Ia definitely, depends, Ia only depends on the load. So when there is zero load, what will be Ia? When there is full load, what will be Ia? And similarly, when there is a change in the load, what will be the change in the torque? I mean, change in the torque that is produced as an output of a motor. So I hope you're understanding me. These two parameters, yes, we are trying to discuss about the relation between those two, and we are making it with respect to the load. As the load changes, what will happen to Ia? What will happen to torque? And then we try to correlate them. I hope you are understanding me. Let me make this statement very clear. So as these three topics, these three particular characteristics, we're going to make the understanding with respect to the load. When the load increases, what will happen to Ia? What will happen to torque? That is about the first one. Now the second one, when the load increases, what will happen to the speed? What will happen to Ia? This is how. And the last one, speed and torque characteristics, also will be analyzing with respect to the load. I hope you are getting me, right? So as the load increases, what will happen to Ia? And then what will happen to torque? I hope you're getting me, right? So now, as the load increases, what will happen, my dear? I hope you know the understanding of load and the current, right? Any motor, any device, when it is heavily loaded, it tries to take more input. So the more input, the more is the load that is kept on the motor, more is the input that it takes from the supply. So in the case of DC motor, when we try to increase the load, the motor draws heavy amount of current. So under no load, the current drawn by the motor is about 5 to 10% of the full load current. What is full load current? Full load current is a rated current that is, described on the nameplate details of any motor. Check out any motor's nameplate details. You find 6 amperes, you find 5 amperes, you find 7 or 10 amperes. That is called full load current. Beyond that, the motor is not designed. The armature conductors are not rated above that particular current. Even if you load motor more than that current, maybe, until 5 to 10% it'll tolerate, but after that rated current, the windings will get burned up. So this is called full load current or rated current. So the motor's current depends on the load. So under no load, the motor takes about 5 to 10% of full load current. Let me make that here. Under no load, it takes 5% to 10% of full load current. So full load current is the one which is on the nameplate details. I hope you're understanding me right. So now, so if you want to understand it clearly, now you see torque. So when the load increases, then what will happen as per this? Yes, the armature current increases. So as the armature current increases, what will happen to the torque? Am I right, my dear? What will happen to the torque? So the torque depends on 2 parameters here. It not only is influenced by Ia, it also has an effect of phi. So a DC shunt motor, now we have to understand about the flux with respect to the load. What happens to the flux? Let me make out a small equivalent circuit of a DC motor. This is actually a separately excited. Shunt and separately excited will always have a similar kind of characteristics. So I have taken a separately excited motor. Now it has got an output power. We have got torque and speed out, and then it takes a current Ia. Let us take the same motor, shunt motor, to avoid the confusion. Okay, there is Ia here and there is If here, and there is a total current that is drawn into the motor. So as the load increases, what will happen? The Ia, the current drawn by the motor, armature will increase. Are you understanding, my dear? The current will rise. Yes, this will rise. I didn't make any statement about If. Am I right? So If, what is If actually? If actually depends on 2 parameters here. If is equals to Vf divided by Rf. I hope you're getting me. So as are you changing? What is Vf? Vf is actually this entire parallel voltage, and that is actually proportional to the supply Vt. So Vf and Vt are same because it's a parallel connection, right? So as the load increases, Ia increases, but there is no comment made on If, because If doesn't relay on this side because it's a parallel branch. The current that is flowing through If is depending on Vf and Rf, so you are not changing the resistance of the field anyways, and you don't have any, you are not changing the supply voltage also during the characteristics of the motor. When this is happening, when the load is increasing, means it is happening when the supply is consistently applied. When the supply is constant at rated voltage conditions, it is running. At that condition, you are running the motor. So your Vt is always constant. So Vt is constant, Vf is constant, thereby Rf anyways it is constant. So If will remain constant. So what would I do here is, what am I taking? What are the implications of this is because If depends on Vf and Rf. Whatever may be the load, whether the load may be 0, whether the load may be full or 50%, whatever the load may be, the field current never changes. I hope you're getting me. Field current never changes. So when the field current doesn't change, then why the flux will change? flux will also never change. I hope you are understanding me, right? So flux is going to be constant in the case of DC shunt motor. This is an easy way of understanding it, very easy way of understanding it. So whatever might happen on the load side, whatever might change on the loading side, so your IA definitely is going to change, but IF will not is not going to change. Because IF is not going to change, your flux is never going to change in the case of a shunt motor. So what will you take here? So shunt motor, I'll write a statement here: flux or constant flux machine. Constant flux machine. It's a constant flux machine. So as the load increases, IA increases. Because the flux is always constant, when the IA increases, torque will increase. Torque will increase. This is what is going to happen there. So now if you want to make an equation between torque, graph between torque and IA, let me take IA on the x-axis and torque on the y-axis, right? And then there is a, shall I make another equation from this? Torque is only proportional to phi, IA, because phi is constant. So it's a linear curve passing through origin. It's a linear curve passing through origin. So this is gonna be torque is proportional to IA. It's a straight line passing through origin. So this is how about the shunt motor side. Now we'll see the same characteristics, this one, number one, on the series motor. For a series take motor, this the characteristics torque versus IA. So how this series motor will exhibit these characteristics, we're going to see that in detail now. So before going further, let me take the equivalent circuit of a DC series motor. Yes, this is the equivalent circuit where you have got an output power that comes out of the motor, which is P0 is equals to T omega. All right. So now it is about armature current, and this is the total current. So this is a field current. Excuse me, this is armature current, and this is your supply voltage. Now you got to test this particular, you got to investigate this particular characteristics for a DC series motor. So what exactly is going to happen here? So as I already said in this particular discussion, that when you are dealing with this characteristic, you should deal that with respect to the load. So as the load increases, we'll see what happens. As the load increases, I'll take it a little down so that I can easily make it. So as the load increases, good. So what will happen? The current drawn by the motor increases, right? But here the current that is drawn by the armature from the supply is IA, and this IA is the same current that is flowing through the field also. Okay, so that's how I can take this equation as IA is equals to IF is equals to I total. It is the same current that is flowing through the entire circuit because it's a series connection. So as the load increases, IA increases, no doubt, because IA increases, your IF will also increase. IF will also increase, and then your flux will also increase. Am I right or not, my dear? So you have to understand the theory here. So in a series motor, as the load increases, the current increases, armature current, and then the field current increases, and then the flux will also rise. So this is a constant flux machine, but this particular motor is not so. It is not a constant flux machine. It is a variable flux machine. So it's a variable flux machine. Okay, variable phi. So because of this change, you're going to have a dramatic change in the entire characteristics. Okay, so now let me try to put up this particular one on the graph. How would it be? How would it be, right? So, well, right. So I'll take on the x-axis. On the x-axis, I will take what is that? Ia, and on y-axis I'll take torque. So unlike this characteristics, here you have, as the torque changes, as the load changes, you have both Ia and flux, both are changing. Both are changing. How are they changing? Because the current that is flowing through the armature and the field, both are same. You have Ia and flux, both are proportional to each other. Hence I can take that torque is proportional to Ia square. So as the load changes, Ia changes, If changes, and thereby phi, which means as the load changes, definitely the current is going to be changed square times. Okay, let us say the current is increased by 2 ampere, then torque will be increased by 4 Newton meter, because whatever the change that happens there in Ia, the same is replicated in the flux, and together it squares up, and then that will imply, or that will affect the torque. So torque will be proportional to Ia square. So what will happen now? So if you want to draw this on the graph, so if you have 2 amperes here, you will get 4 Newton meter torque here. If you have 5 amperes, yes, 25 Newton meter. It's going to be a hyperbolic function there. So then, it's going to be like this. But hang on, it doesn't continue in that direction for a long time. The reason is, you have to understand a point here, a very important point. So when the current is rising, through the armature, yes, the field current is also rising, and the field current is proportional to the phi, no doubt in that. But the aspect of interest here is, as the current is rising through the field, if as Ia is increasing to the higher levels, the flux that is supposed to increase along with Ia, along with phi, If, whatever, both are same. The flux which is supposed to have same increments as Ia will not, or will stop having that proportional change as it moves on to the higher levels. I hope you are getting me. So flux will not rise as expected, because of the reason that the flux gets saturated. In fact, the field winding gets saturated. Any coil, any electromagnetic coil, since when it is invented in the year of 1821s, even before 1820. So since then, the problem of a magnetic circuit, electromagnetic circuit, is that it is subjected to a condition called saturation, a flux saturating condition, and that is going to affect the DC series motor now. Okay, so maybe there will be, until this point, let's say you have about 5 amperes of armature current changed. After 5 amperes, if you further see the load is increasing, so maybe the current still will rise from 5 amperes to 6 amperes, but because of the saturation of the field, the flux will not rise afterwards. Meaning, what will happen? Until one point of one particular value of the armature current, torque is proportional to Ia square. After that, the torque is proportional to, you have to understand this point very clearly, my dear. Torque is proportional to only Ia, because flux will no more increase anyway. The flux will no more have any changes after 5 amperes. So until 5 amperes, before saturation, you have torque proportional to Ia square, because phi is proportional to Ia, because phi changes with respect to Ia. Phi will respond to the current changes. But once the flux or field gets saturated, so then during this region, the torque will no more be proportional to Ia square, because phi is not going to change anyway. Phi is going to be constant with respect to the load now, with respect to any changes that happens in an Ia. Flux will not respond, so it will become like a shunt motor during saturation region, in the saturation region. So it will be like a straight line from there. I hope you are understanding me, my dear. So until this particular point, it will be like a hyperbolic function. A sudden rise will happen, a sudden steep rise, but afterwards you have a straight line that happens here. So I would say that until saturation, the motor, the series motor will exhibit torque proportional to Ia square, will exhibit the characteristics of torque and Ia with square times. But once the field gets saturated, once the saturation current point is exceeded, then the motor will have a linear characteristics for speed, for torque and Ia. So it will be like a shunt motor again altogether. I hope you are understanding me. So the aspect of flux saturation is very important in the case of characteristics of a DC motor. So that's how this saturation of flux is one way it's very good. Okay, the saturation of flux, the saturation flux is one way is very good. You're going to have a linear characteristics for between torque and Ia. As long as it is in normal range, you will be exhibiting a higher torque values. So this is how your understanding, you can understand about the torque versus Ia characteristics for shunt motor as well as for series motor. I hope you understand this. And number 2, what is that? Speed and Ia, we're going to see in the next session.